Welcome to this Mickey Mouse lecture. I want to present some theorems in graph theory dealing with manifolds, d-manifolds, discrete d-manifolds. Remember, a discrete d-manifold is a finite simple graph such that every unit sphere is a d-1 sphere, and inductively defined also a d-sphere is a d-manifold such that if you take away a vertex, then we get a contractible graph. And the graph is contractible if we can take away a vertex with a contractible unit sphere such that the remainder is also contractible. And that's all primed with the assumption that the empty graph is the -1 sphere and the 1-point graph is a contractible graph. So this produces discrete manifolds. We have 10 theorems here, which I just present also somehow not to forget them. And so it's kind of a memo for myself. Again, it's also a little bit more of a technology test or technology practice. So let me get started with number 1, which is a sphere theorem. It's a baby version of the big theorem of Klingenberg-Berger. A positive curvature compact Riemannian manifold which is orientable has to be a sphere, provided that the curvature satisfies some pinching condition. The pinching condition, optimal pinching condition, is 1/4, and it has been conjectured by Hopf in the 30s, and then Rau, who visited ETH, has given a proof for in the case of a 3/4 pinching condition, and then Klingenberg and Berger, they have just found the optimal version. There is also a differentiable version, which was quite recent, 2007, and I was working on this in the discrete. Since maybe in 2011, I made a list of all positive curvature 2 manifolds. So there are 6 of them, like the 6 Disney figures here. And then in 2019, looking at the general case, so assuming positive curvature means that every embedded wheel graph has 4 or 5 vertices. So these are positive curvature vertices, right? So if you have a two graph, a 2 manifold, and the point has just 4 neighbors, then cyclic graph with 4 elements, then the curvature is, in this case, the curvature is 1/3. So it's this Levitt formula which we have seen, 1 minus the number of vertices divided by 2 plus the number of edges in the unit sphere divided by 3. And that's just 1 minus the degree of the vertex divided by 6. It's a very old formula which has been used in graph coloring. We will come to graph coloring in a second. So that's the strongest positive curvature which we can have. We cannot have 3 vertices because otherwise we get the tetrahedron and we get a 3-dimensional graph. So that's not allowed. This is curvature 1/6, 1 minus 5, 6. And then we have a 0 curvature. If you have 6 neighbors, that's 0 curvature. It's flat. And if you have more, 7, 8, 9 or more, then it's negative curvature. This is a case of a negative curvature disk. The theorem is very simple, so it's really a Mickey Mouse theorem. It's completely unpublishable because it's so simple, but it's kind of cute, because what you have to do is you have to understand if you have an embedded 2-dimensional surface or a geodesic surface. If you have in the continuum, if you have positive curvature, means that if you start geodesic flow in a 2-dimensional plane at the point and you let all these geodesics move, you get the surface, and this surface has positive curvature at every point and in every possible direction. That's a very strong condition, and there's an unsolved problem of Hopf also, whether this implies that the Euler characteristic is positive. So in this case, when the curvature is 1/4 pinched, then yes, that because of the sphere theorem, because the sphere has in even dimension. So the sphere in even dimension has an Euler characteristic too. So how does the proof go of this result? It's a Geomark argument. Yeah, positive curvature means that every embedded wheel graph has 4 or 5 vertices. It's a very strong condition. It's actually a 1/2 pinched, right? Because this is 1/3, this is 1 1/6. So this means it's necessary 1/2 pitched. And it's kind of surprising that we don't need the orientability assumption. And I can give you quickly the argument why this is not needed. One of the reasons is, or the reason is that if you want to make something non-orientable, you have to have a chain of triangles which turn around. The smallest number of vertices with which you can realize this turning is 7. And 7 vertices with a curvature 1/6. That's the minimal curvature which we can have, right? So then you have already Euler characteristic 7/6. So the Euler characteristic is an integer. So you cannot have the projective plane, which is Euler characteristic 1. But there's not enough space to turn around things. We don't need the orientability assumption. We also have automatically Sinch theorem, which says that we have a simply connected space, and but that follows also from the theorem. But how does it work? You start with some point and you build this wheel graph. And now what you can do is you can continue here. You can continue with this Gilmark construction, and you can add another. You can continue building the surface. Now this is not unique, like geodesic surfaces are also not unique. I mean, you have to make some choice here. But what happens is, however you continue, right? 1, 2, 3, 4, 5. So we have actually, in this case, we have to kind of do this. We are forced to close it here up, so to have positive curvature. Now, if you have everywhere positive curvature, what will happen is you will produce a surface which has to close up. If you build this surface, they are just the maximal version which you can get is when the curvature is minimal everywhere, when it's 1/6 everywhere. That's the icosahedron. In the icosahedron case, that's a graph with a diameter 3, and in the case when the curvature is everywhere maximal, 1/3, then you get the octahedron. So between this octahedron and the icosahedron, you have 6 possibilities. In total, six possible graphs. But they all have diameter 2 or 3, so they are very small. That's why it's called Mickey Mouse. And what happens is this happens when you take a higher dimensional space, right? So this is a 3-dimensional sphere. So this is, I printed that myself. It's very, very bad, too thin connections here. But so this is a 3-sphere, and what happens is, if you take a point and a 2-dimensional direction, meaning a wheel graph, and you build then this Gilmark construction in any way, so it can be done in many, many different ways, but if you do that, you get a 2-dimensional surface which has diameter 3. Now what you can also prove, and that's also part of Gilmark, kind of this Gilmark construction, if you have a closed curve in this space, what you can do also, you can build around this curve, you can build a surface. So what you can do, I mean, this has to be a subgraph also of the original graph, so you can build a surface, and whatever you do, and this positive curvature forces you that this curve will actually be on a 2-dimensional sphere embedded in the graph. So the diameter has to be 3 also. So that limits the diameter of the whole space. So independent of the dimension, the diameter can be only 3 or less. And then comes another argument, is that if you look at the ball of radius 2, that needs positive curvature too. If you take a ball of radius 2 in 2 dimensions, this always is either it closes up to an octahedron already, or it is a 2-dimensional ball with a 1-dimensional boundary. So this is something this is not true if you allow negative curvature. If you allow negative curvature, you can have at the boundary some identifications, and you get already here some closed curves on the identified points. So what this means is you take a point and you take a 2-dimensional ball, and then you take another point in distance 2, or if the diameter is 3, distance 3, and you build another ball of radius 2. So what happens is they have to intersect and they overlap the whole thing. So what you have done is you have covered the entire sphere, you have covered it with two balls. And whenever this is possible, then you have a sphere. We will come to this, it's essentially Reeb. So you can also see that if you take away one point here, then you have a contractible space. So that's the reason. So that's by definition a sphere. But it's pretty cool, and so it essentially gives you kind of a feel for why the sphere theorem holds also in the continuum. In the continuum you can do the same thing. You just take a point and then you let the geodesics flow, and then you can continue that flow in such a way that at every point you are kind of close to that. So what you get is you get embedded spheres, and the diameter of these spheres are, you can estimate the diameter of these spheres. So they have to close up. And that's actually already the argument of Rauch. And so you see positive curvature means that geodesics focus again. So they will close up. You will get two-dimensional spheres. In 2 dimensions, it's kind of, it's clear. That's the number one. Okay, number two, already 2 weeks ago I was talking about this Morse Sard theorem. It's a very surprising result that if you have a d-manifold, as we have defined it, a class of graphs which locally look Euclidean, so that every unit sphere is a d-1 sphere. And if you look at the function, which is a coloring, which is locally injective, then you look at the level surface, which is the subgraph of the barycentric refinement. This is always a d-1 manifold, or empty if there is no place where the function changes sign. F minus c changes sign. So that's a result also from the 30s, 40s, and I proved this in 2015 in this framework. Oh, Mickey Mouse. So that's the Morse Sard result. Maybe I'll show you an example of a surface. I was actually interested in this case because of level surfaces of eigenfunctions of the Laplacian, which is an interesting topic. So when you look at eigenfunctions, what are these level surfaces? So that's an interesting study, and still not much understood. Not only the eigenvalues are interesting, also the eigenfunctions are interesting. So you want especially also to know how they are their geometry. So an example here, maybe just an example here, if the function has a maximum somewhere, maximum 10, and the next smaller function value is 9, and you take the function f is equal to 9.5. So what you get is every simplex where the function changes sign. So this contains this simplex, this triangle, this edge, this triangle, this edge, alternatingly edges and triangles, edges and triangles, edges and triangles, and you get a cyclic graph. So the level surface is a cyclic graph. By the way, that's not the same Morse than from Morse theory, that's Anthony Morse. Cool. The next theorem is very interesting in topology. It's the Jordan-Brouwer theme. So when you have a sphere in another sphere, then it divides a d-1 sphere in a d sphere, then it divides the region into two parts, and both of them are balls. So maybe just this is a sphere here, and I put another sphere inside. So I put another sphere inside here. So what we have is we have the inside, which is a ball, and then the outside of that is actually also a ball. So what you have in 2 dimensions, it looks obvious, right? You have a closed curve. So what is a circle? This is a circle embedded into in a 2-dimensional sphere. So this is a 1-dimensional sphere in a 2-dimensional sphere. So what it tells you that this curve will divide up the region into 2 parts, and both parts are balls. It's kind of obvious if you take the equator, right? And you have just two half spheres, hemispheres, which are balls. But it's actually not so trivial, and there are lots of deep results here. I mean, this Schoenflies is actually kind of, you need some regularity in the continuum so that works. And there's a theorem of Mazur, Morse, Brown, which shows that if the manifold is nice enough, P out, and also the level surface has to have this d-1 sphere, has also to have some regularity. This Alexander Hall sphere is an example of a sphere, embedded sphere, where one of the parts is no more simply connected. So it's definitely not a ball. So this is highly non-trivial. And the Jordan theorem, the Jordan in 2 dimensions, that's the Jordan curve theorem, is surprisingly hard. And but Jordan's proof was discredited for a while until it was rehabilitated, and it's essentially correct proof. And this theorem has also been proven in the meantime by computer verification, computer verified proofs. So this is but it's surpringly tough. In the discrete, it's much easier because you have no technicalities, so you have essentially a very regular situation, polyhedra type situation, and that's also kind of but the difficulty is already also in the continuum is to verify it for discrete approximations. And what you have to verify is, and you have this. What you do, I mean, the idea is you take this sphere, you take this embedded sphere, and you deform it until you get to a point. And when you can do that, when you can deform it to a point, then you know, and you take a point away, you have one ball, and that also is a ball. I mean, discrete, a unit ball is already a ball. So what you do in the discrete, you actually also do a homotopy deformation of the curve. But then you have to say clearly what the homotopy deformation is. So, for example, if you have a curve like this, and so what you are allowed to do is you're allowed to replace a path in a simplex by the complement in the simplex. So you move from here, you move to that, and so on. So what you can do is you can deform, and then what you verify is that the intersection number. If you take a curve which intersects a curve, you define an intersection number precisely, and then you show that under these homotopy deformations, this intersection number does not change. So then when you go from one to the other, so when you have a closed curve, you have to go an even number of times, you have to cross over. So it's not possible that during the deformation something strange happens, and like with the sphere inside out, they're all kind of non-intuitive thing. You can turn the sphere inside out, inside outside, without actually ripping it apart. So there are some strange things which can happen in topology. One has to be careful, and usually the right way to do this is using invariants, integers which do not change under deformation, and then you are fine. So so there are quite many versions of the Jordan-Brouwer theorem in the discrete, but usually they assume something like a grid graph or some kind of not a general graph theoretical result like here. So this is the Jordan-Brouwer theorem, which is also part of knot theory, because a sphere embedded in another sphere, that's kind of a generalized knot, and one sphere embedded in a 3-sphere is a knot. So this is Jordan-Brouwer. The next result is very old. But it's due to Poincare, and Lefschetz has then also dealt with a case with boundary. But what it says that these Betty numbers are symmetric. There's a symmetry with respect to the Betty numbers in the case when you have an orientable manifold. So that's surprisingly subtle, because what you have to do is you have to get from a graph, you have to get the dual graph. But if you take the dual graph of a sphere, that's no more a sphere. right? In our definition, because what you have, for example, when you take the right, if you take the three-dimensional three sphere, which is the smallest three sphere, which is a cross polytope, and you take the dual, you get the tesseract. We get the three-dimensional cube. So that's no more a three sphere, right? Because the unit sphere is not a sphere, right? So that's that one has to be very, very precise about what one calls a sphere. And actually, Poincare himself kind of battled with this for about 3 years. Hegardt was one of the mathematicians who were objecting to the first thing. So what you can do, and that's actually quite nice. I like this, to see this actually a little bit differently. When you look at the d-manifold, what the property is that if you take a simplex and you take the intersections of all unit spheres of a simplex, what you get is always a sphere. This is called the stable sphere. So you have this hyperbolic structure, which is the stable and unstable sphere. The stable sphere is of a simplex is just the boundary, and the unstable part, everything which contains this simplex. So what you have is, you can write the unit sphere, you can write it as a join of the stable sphere with the unstable sphere. So what happens is kind of when you have a vertex itself, the stable sphere is the minus one sphere. It's the empty graph, and this is the unstable sphere. What happens if you have an edge here? Then the intersection of this sphere with this sphere is actually a zero sphere. It's 2 points. So in the barycentric refinement, and that's always kind of how you should think. In the barycentric refinement, what happens is the unit sphere of that edge, that's a cyclic graph with 4 elements. And that's the join of the stable sphere with the unstable sphere. So what happens is this Poincare duality is you just go from the stable manifold to the unstable manifold, and you don't think about simplicity complexes. What happens is then this unstable sphere is not a simplicity complex by itself, but you have to identify the simplex to a point, put it together to a point, and then you get the simplicity complex. So what you have is kind of some kind of generalized duality. So classically, this is done with CW complexes, or if you take a complex, you take a simplicial decomposition of a space, and then the dual is a CW complex. You just have a collections of cells attached to previously constructed things. I like the story of the spheres. So I'm a little bit like a sacred geometry. This is a sacred geometry symbol there. Sacred geometry is obsessed with spheres. And so spheres are actually the structure which really works very well in the graph theoretical settings. There are no lines or planes and things like that, but what you have is spheres, or unit spheres, and you can define very clearly what the sphere is. So that's pretty cool. What happens in the case of discrete manifolds, if you take a simplex and you take the intersection of all unit spheres of a simplex, you get a sphere. So that's pretty cool. And it definitely needs that the manifold is orientable. Otherwise, it's not true that the projective space. This is Betty vector 1, 0, 0. So the two-dimensional sphere, it's 1, 0, 1. And so that's for spheres. You have this. It essentially means palindromic here, right? And we come to palindromic here, and actually this is related. This Dehn-Sommerville relation, which we come to, is related to Poincare duality, but it's much more general. It's actually kind of does not. This holds also in situations where we have no manifolds, but we will just come to this. I don't think in the discrete there's anything new. So Poincare was thinking already like a graph theorist, or like a combinatorial in combinatorial terms. Yeah, Dehn-Sommerville is a very exciting topic. So Dehn-Sommerville, I got in touch with Dehn-Sommerville several times in completely different ways. And more recently, I was interested in in this f function. So the f function is equal to 1 plus f0 t plus f1 t squared plus fd d plus 1, where fk is the number of k-dimensional simplices, complete subgraphs in a graph. So this is defined for any graph, and what is nice is this has nice properties. And so what I was interested in, what are the roots of this function, what are the symmetries, actually turns out, as you saw for spheres, it's always at 1 minus 1/2, there was always a root. And so there was something going on. And then I realized that just for spheres you have always this symmetry. I don't think this has been actually pointed out before, but this is pretty cool, because what it means is the roots are symmetric with respect to 1/2. And then what you can do is you can define this function here, which is now a palindromic polynomial. You can just verify that by from the roots, because of the roots because of what you know what the roots are. And then you get to this coefficients here are what one classically has considered as in the Dehn-Sommerville relations. But it's always with these binomial coefficients, always complicated stuff. So this is much more elegant if you just work with functions. And so this we have seen last time this general Gauss-Bonnet theorem, which tells you that the f function of the graph is actually a sum of integrals of f functions of the unit spheres. So this implies that if all unit spheres are Dehn-Sommerville, then also the manifold or the graph itself is Dehn-Sommerville. So this is pretty cool, because what it tells you is that so you can construct Dehn-Sommerville spaces which are much more general than spheres. It's also what follows from this, the f function it multiplies under joins, so that this is actually a monoid. You have like spheres, you have a monoid of Dehn-Sommerville spaces. And you can define this recursively. You can start with the empty graph, and you say kind of that's x0, x1, xd is defined as x offset that all unit spheres are in xd minus 1. And you have also to make the assumption about the Euler characteristic. Then you are fine, and you have a kind of a space of graphs, which is very, very natural, sphere-like spaces, much more general than spheres. And spheres need homotopy to be defined, I've seen that, but that's purely combinatorially defined. That's also responsible that in the case of discrete manifolds, the curvature is actually 0 for odd dimension manifold, which then also implies the Euler characteristic is 0. It's pretty cool, and it kind of has been developed more than 100 years ago and then rediscovered in the 60s, and it's now big in every book on polyhedra, polytops. But it's usually considered for spheres, so kind of discrete spheres, and not for not in graphs here. Okay, so that was number 5. Now for number 6, it's a little bit some very classical topic is planar graphs and coloring of planar graphs. And the 4-color theorem is a very famous theorem which says that every planar graph can be colored with 3 or 4 colors. But then it turns out with this theorem you see that kind of it's the hardest thing is to color a maximally planar. If you take a planar graph and you extend it until it's maximal, you cannot more extend it, that's called maximally planar. And then you also want four connectivity. Four connected means you can take away 3 vertices and still connect it. So it should not have a neck. If I take this K4 here, that's still 3 connected, because what I can do, if I take these 3 away, I'm still connected. But Avicii graph, so if you have this is not 3 connected, because you can take these 3, this neck you can take away, and then it becomes disconnected. And then if something is not 4 connected, what you can do, and that has been discovered several times, that's essentially everybody working in this field has discovered that at some point. You can do the coloring on this side and you can do the coloring on that side, and then you can put things together. Proving the 4-color theorem for 2 spheres is actually all you need. Appears to be a simple way to actually see the 4-color theorem. You make it to a ball, And then you start refining the inside more and more until everything inside is Eulerian, in the sense that the intersection of two unit spheres, adjacent unit spheres, always has even cardinality. It has to be a one sphere, but it has to be have even cardinality. And if that is happening for at every edge, what you automatically have, then you can color the inside with 4 colors. And then when you do that, you never touch the boundary. You do all these refinements, and then you have covered the inside with you have everything colored with 4 colors. That gives you a coloring on the outside. Okay, number 7 is a result which in 2 dimensions has been found by Whitney, and then Tutte generalized it. So this graph is planar graph, but it's not Hamiltonian. These points here you have actually to reach, right? So you have to go through these points. The Hamiltonian path has to go through. So what happens is now you cannot have no choice, right? When you come here, you have to go here. So you never reach that point here. So this is a graph which is non-Hamiltonian. But what happens is if you extend it to a two sphere, we have a Hamiltonian graph. Now I proved in general that a d-manifold is always Hamiltonian with or without boundary. And it's actually quite a simple argument. What happens is what you do is you go by induction in D. So what you take is you take your manifold and then you cut out holes. It's a Swiss cheese argument. You cut out holes. So what you get is still a manifold with boundary. All of these holes are smaller dimensional spheres. So you can find a Hamiltonian path in each of them. And then what you do is you connect them. So you can just make a detour here. Either you go from, and you can build bridges. So you can go around, and so that you can connect all of them. And then finally, it might happen that there are some points inside which have not been reached. So in this case, you would have to just extend that a little bit. That's a inductive proof with respect to dimension. The 8th result is a characterization of spheres. So a sphere you can characterize as a manifold which has admits a function with 2 critical points where level curves are all one-dimensional spheres. If you have a manifold which admits a function which has 2 critical points and only 2 critical points, it has to be a sphere. So that's how you can characterize a sphere. And it doesn't even have to be nice. It can also be degenerate. So in the discrete, this is actually just a little bit of justification why this notion of spheres, which is due to Evacco, this homotopic definition of sphere, is the same thing than Forman's definition of which uses functions. You can actually in the discrete also define spheres like that as graphs which just admit a function which has 2 critical points. So in some sense this also says that spheres are category 2, Lusternik-Schnirelmann category 2 manifolds. So there's so the minimal number of critical points is always bigger or equal than the category number of patches, contractible patches you need to cover the entire manifold. So in our case, we need 2 patches to cover the sphere, and they also there's an equality. The next result doesn't have an analog in the continuum, and it deals with the Wu characteristic. So of a graph, this is some x, y, omega x, omega y. So omega x is -1 to the dimension of x. And x and y are complete subgraphs. So what happens is if you take a manifold with boundary, then the Wu characteristic is just the Euler characteristic minus the Euler characteristic of the boundary. What happens is if you have no boundary, then the Euler characteristic is the same than the Wu characteristic in the discrete manifold case. And also because of odd-dimensional manifolds have 0 Euler characteristic, it's also for even-dimensional manifolds. Even-dimensional manifolds with boundary, then the Wu characteristic is the same thing than the Euler characteristic. So about this Wu characteristic, this has been defined in the 50s. Grünbaum kind of pointed out some, made it more precise in the 70s. I was kind of started to work on this in 2015. And finally, that's something I talked about in a math table. It's kind of a very silly story somehow that the Euler characteristic of a sphere is, it depends on the dimension. So in even dimensions it's 2, in odd dimensions it's 0. One has to be very clear what one actually means with a sphere. So, or what one means with a polytope. So this is usually when you look at these results, has been done for Platonic solids. If Descartes was looking at Platonic solids, he was just observing that there is this relation that v minus e plus f is equal to 2. So that's in dimension 2. And Schlaefli figured out those things in higher dimensions. Schlaefli was the first who actually started to kind of really do seriously geometry in also higher dimensions. But one has to be careful what one takes as the definition. So this is a hypersphere. This is also called the tesseract, and in this case, this is not the 3-sphere yet. You have to stellate it. You have to kind of triangulate it, make it clear what you mean with faces. 4-dimensional sphere, which is obtained as a result. So in 4 dimensions, it's again 2. This also works then. This formula then also works for homotopy spheres. A famous homotopy sphere has already been defined by Poincare. So he was looking at the dodecahedron. So it's a field dodecahedron, not just a boundary. So it's a 3-dimensional ball. And now what you do is you identify on the boundary. You identify these faces with the face, with this face, with this face, and so on. So if you make all these identifications, you get the 3-dimensional sphere, but it is not equivalent to the standard sphere. So in this case, you can build a graph, and you see this homology sphere. The unit spheres are these are manifolds. This is 2-dimensional. What I was not yet able to compute here, unfortunately, because it's too big, but the Wu homology. So that's kind of just the matrices are becoming too big. And that's it with this 10 Mickey Mouse theorems.